So let's start the session. This is week 12 online live session for the NPTEL course on Urban Utilities Planning, Water Supply, Sanitation and Drainage. The course instructor is Dr. Devapratim Pandit. He is a professor in Department of Architecture and Regional Planning at IIT Kharagpur. I am the teaching assistant for this course. I am Vaibhav Kabadwal. I am a research scholar in the Department of Civil Engineering at IIT Madras. So this is the lecture outline. So we will understand or solve some questions on drainage and recharge. That is, and we will understand groundwater recharge, and we will do the revision of the course also. Let's start. Excess groundwater results in recharge means like our phones, we recharge them. So likewise we will recharge the groundwater depleted, which is exploited through pumps or something. So let's understand what is recharge. So this is groundwater, uh, ground level, and this is groundwater table. So if you have made a well, you will continuously take out the water, and if it is industrial requirement, then we will take out more water, and in that case the groundwater level will deplete. So to increase the groundwater level, we do rainwater harvesting, and we have so many methods. Due to that, we can recharge the groundwater table. So this is called recharge. So we can write it like sorry. It is called depletion. It is called recharge. So excess groundwater recharge results in, so if the water further it is recharged, then it can cause water logging. So the answer is water logging. Match the illustrations with the recharge technique and choose the correct set from the options. So trench is this. Trench is this one. R is I, first one. So trench will look like, it's, if you make it in 3D, it will look like this. Trench are made in a line like this. Water will flow like this. So this is trench. And this is a well. From top view it will look like this circle. So these methods can be used to recharge the groundwater table. Trench is third one. Aquifer well is second one. This is second one, aquifer well. And this one is excavated basin. P is second, Q is third, R is first. So B is the correct answer. B is the correct answer. Storage of stormwater runoff on site to allow for sedimentation of suspended solid is called. Storage of stormwater runoff site to allow for sedimentation of suspended solids is called. So what happens? The runoff, it is runoff through a slope, let's say. This is the runoff. runoff. The storage of uh, stormwater runoff on site to allow for sedimentation of suspended solid is called. So what will happen? So this is the slope where the water is coming, and we provide one depression to allow the sediments to settle. Sediments to settle, and then again the water will go. So here sedimentation, this is called retention. Which of the following processes utilize phytoremediation or bacterial colonies to metabolize contaminants in stormwater runoff? Which of the following processes utilize phytoremediation or bacterial colonies to metabolize contaminants in stormwater runoff? This is treatment. In secondary treatment, secondary treatment secondary treatment we use microbes. Groundwater depletion is due to, we understood about the depletion, so indiscriminate abstraction of groundwater. In Rajasthan, Gujarat, Tamil Nadu, Punjab, Delhi, Haryana are severely affected due to indiscriminate extraction or abstraction of groundwater, and traditional water harvesting methods have been abandoned. We are not using the water harvesting methods, so that's why the depletion is going on. How steep water level decline can be immediately controlled. Shifting of abstraction to floodplains where high yield tube well can be sustained. First thing we can do, recycling and reuse of water. So if we recycle and reuse the water, we don't have to abstract or extract water from the groundwater. And we should have dual water supply system, that is one for drinking and other for and second for other domestic uses. So what we can do, drinking, we can provide fresh water, that is drinking, that is groundwater, and other domestic uses we can recycle the uh, uh, water which we are producing as a waste. And third, we can do rainwater harvesting and other measures which can be implemented through regulatory monitoring and enforcement. So regulatory means we can provide policies, and monitoring we can do some inspection, and enforcement can be done with the help of fines. So if we can do these three things, then we can decline the uh, groundwater depletion. When surface storage is not feasible. When surface storing is not feasible. So surface storage means this is the ground and you are storing the water in the pond. Let's say this is the pond. So when it is not feasible, so what is evapotranspiration? Let's understand. So here there are trees. So evaporation and transpiration is called evaporation and transpiration come combined, these are called evapotranspiration. So near the cropped area, this term is mostly used because from the crops there will be transpiration, and from the soil it is evaporation. So for a cropped area, this term is used for this term is used for the cropped area, and mostly in agriculture. So when evaporation is more, the water will go and form clouds, and if rainfall is less, so then this will not be feasible. So it is not feasible when evapotranspiration is more. When evapotranspiration is less, then it can work. A is the correct answer. Too much recharge can lead to waterlogging, that we understood. So these are the methods for hilly areas. Like bench terracing is the water recharge method. So in bench terracing, we'll cut the hill in step stepped way so that water can pass like this manner, and the soil can absorb the water. So water will be so the velocity will be decreased, and water can pass slowly, and it is a method for agriculture also. So bench terracing is done for agriculture, for uh, water, what to call it, water recharge. So this is helpful in agriculture also. So, and it is a method of water harvesting. Gully plugging, this is also used in hilly area. So what is done from the channels, like channels which are available in the naturally available on the hill slope. So these are plugging is done with the help of stones that can stop the or reduce the flow, and the water can percolate into the soil. Contour trenching. So to arrest the water, suppose this is the flow. To arrest the water, so to arrest the water flow, suppose this is the water flow. So water is going this way, this way. So we are arresting the water, and the water will go through this path, and we can channelize this water to our fields. So this is a method of like water harvesting, we can say, and mostly it is used for the agriculture. Cost of groundwater recharge project includes. So the cost includes cost of investigation. You have to investigate where to put the water recharge structure, how is the flow, how is the topography. So investigation is that, and source of water, from where the water is coming, and whether treatment is required. Construction of recharge structures. So what is the cost of the recharge structures, and operation and maintenance. So these all include into the cost of groundwater recharge projects. What is the full form of CGWB? CGWB is Central Groundwater Board. Which one of the following products is not obtained in anaerobic decomposition of glucose? So glucose is C6H12O6. So uh, it can form these things, but H2S will not be formed because sulfur is not available. This is correct. So during anaerobic decomposition, hydrogen sulfide will not be formed. Crown corrosion in a reinforced concrete sewer is caused by. So let's understand what is sewer. So sewer are the pipelines which are used to carry sewage. So it has sewage. So Sewage, uh, sewage is under mostly anaerobic condition, mostly under anaerobic condition. So this because it has limited supply of oxygen under the ground or inside the pipe, those sewer pipes. So because of this anaerobic condition, the organic matter which is being carried in the sewer pipelines will undergo anaerobic decomposition and it will form methane and H2S. So that H2S is corrosive in nature, and that will corrode the pipes. So the reinforcement, so the concrete is so the pipes are made of reinforcement bars. The pipes are made of reinforcing bars. So these pipes are made of reinforcing bars, that you can understand, and this because of the decomposition of this organic matter, H2S will form, and H2S will go up as it is a gas, and it will attack the steel bars. And steel bars will corrode, undergo corrosion, and that is called crown corrosion. This is called crown corrosion. So H2S is the main gas which causes crown corrosion. True or false? At a manhole, the crown of outgoing sewer should not be higher than the crown of the incoming sewer. So this is called crown. This is the top part is called crown, and this bottom part is called invert. Sewers. At a manhole, the crown of the outgoing sewer should not be higher than the crown of the incoming sewer. So this is the manhole. This is incoming sewer. This is the outgoing sewer. This is case A. This is the case B. This is the incoming sewer. Dia, we are not considering dia. Okay. This is the outgoing sewer. So which one is correct? Check and tell. This is outgoing sewer. If in case B, water will first fill here and then it will go here. Then backflow can also occur in the second case. So backflow. That's why what is the statement? The crown of the outgoing sewer should not be higher than the crown of the incoming sewer. So it should not be higher. It should not be higher than the incoming sewer. Because the statement is true, because to control the backing of sewage in the incoming sewer, the crown of the outgoing sewer should not be higher than the crown of the incoming sewer. This is the reason. We have a question here. A sewage treatment plant receives sewage at a flow of flow is 5000 meter cube per day, and the total suspended solids are 200 milligram per liter. And after the primary treatment, TSS, so the primary treatment, TSS concentration in the sewage reduced by primary treatment, the TSS concentration reduced by 60%. The sludge from the primary clarifier contains 2% solids concentration. Subsequently, the sludge is subjected to gravity thickening process to achieve a solid concentration of 6%. Assume that the density of sludge before and after thickening is 1000 kg per meter cube. The daily volume of thickened sludge will be. So the question is simple. The sewage treatment plant receives this much volume per day, 5000 meter cube per day. The total suspended solid concentration in the sewage at the inlet of the primary clarifier is 2000. So the TSS, total suspended solid concentration, is 200 milligram per liter. And after the primary treatment, the TSS in the sewage reduced by. So in this, the efficiency of primary treatment is 60% and the effluent will be 40%. So in the primary treatment, or in the primary clarifier, so removal in the prime, let's make a new slide. This is primary clarifier. So it will contain 2% solids. Its efficiency is 60%. Okay. And after this process, it will undergo thickening. After thickening, it will contain 6% solids. Means water is getting removed. Water is removed in the thickening, and the percentage of mass of solids will remain same. Mass of solids will remain same, but the water is removed, so the percentage of solids increased. Mass of water removed and solid mass remains same. That's why remains same. Solid mass remains same, and so that's why the percentage increases. So what the question is asking, so the daily volume of thickened sludge in meter cube per day will be. So what is the volume which we, so how much volume we are getting? Volume of thickened sludge which we are getting. Thickened sludge. So let's understand. Insert total solids. Total solids were 5000 meter cube per day into 200 gram per meter cube. So it was given 200 milligram per liter. 200 milligram per liter can be written as 200 gram per meter cube. Understood? So we can write it as ten to the power 6 grams per day solids, and 60% removed in primary clarifier. Removed in primary clarifier. That will be 0.6 of 10 to the power 6 grams per day. So it will be 6 into 10 to the power 5 grams per day. And these are the solids which are coming out from PST, and this much amount of solids are available in sludge thickening also. So this much solid is 6%. 6%. These solids are 6%. 6% after thickening. So these solids are 6% after thickening. So 6% of total V is the volume, is how much? 6 into 10 to the power 5 grams per day. The volume will be 10 to the power 5 plus 6, 7 grams per day, or we can write 10 to the power 4 kg per day. This is the volume of sludge after thickening. Volume of sludge after thickening is how much? 10 to the power 4 kg per day. Kg per day. So, but answer is in which form? Meter cube per day. So we have to convert the weight into volume, and we have been given here like assume the density of sludge before and after thickening is 1000 kg per meter cube. So we know the density is 1000 kg per meter cube, and you will divide it by density of thickened sludge, that is 10 to the power 3. You will get 10 meter cube per day of thickened sludge, the volume of sludge after thickening. We can write volume of sludge after thickening is 10 meter cube per day. The answer is 10. Next question is, total hardness in raw water is 500 milligram per liter as CaCO3. So the total hardness is 500 milligram per liter in terms of CaCO3. The total hardness of this raw water expressed in milli-equivalent per liter is. So we have to express it in terms of milli-equivalent per liter. So it is in the form of CaCO3. So first we'll calculate what is the molecular weight of CaCO3. So molecular weight of CaCO3, that is 40 plus carbon, it is 12, and oxygen is 16 into 3. We solve it, we will get it 100 grams equivalent. So CaCO3, Ca will give Ca 2 plus and CO3 2 minus. So its valency is 2, and so we'll get the equivalent weight equivalent e- equivalent weight we need to calculate. Equivalent weight is molecular weight by valency, that is 100 divided by 2, so we'll get 50 grams is the equivalent weight. Now we need to calculate milli equivalents. So we'll calculate equivalents. Equivalents is defined as like moles. Moles means given weight by molecular weight. So equivalent means given weight similarly by equivalent weight. So given weight is 500 milligram and equivalent weight is 50 grams. So 500 into 10 to the power minus 3 grams by 50. So I can write it as 10. This is the unit will be in equivalents. And this 10 by 3, if I combine these two, I will call it as 10 milli equivalents. So the answer is 10 milli equivalent. Correct. The answer is 10 milli equivalent. A 50 ml sample of industrial wastewater is taken into a silica crucible. The empty weight of crucible is, so what we are doing, let's understand the question. So these are the crucible, will look like this. So initially the 50 ml water is taken in this crucible. So volume is 50 ml of wastewater or water is taken, and the empty weight of crucible is taken is weighed as 54.352 grams. The crucible after this sample, the crucible with sample is dried in hot air oven at 104 degrees Celsius. So after the 50 ml water is kept, it is dried at 104 degrees Celsius for 24 hours. The time is not given, but at least we do it for 18 to 24 hours, and then some residue will be left here. That we call it total solids, and that weight is 55.129 grams. Thereafter, the crucible is again fired. So initially 104 degrees Celsius, then again fired at 600 degrees Celsius for 1 hour in the muffle furnace. And then what will happen? I'm just making it small. So the organic or volatile compounds will volatilize. Organic compound will volatile. So that will be formed in the form of, that will go into the atmosphere in the form of CO2 and other forms. So only inorganic here, inorganic residue will be left. Inorganic residue left behind. So W2 was this, and W3 crucible with residue determined as 54.783 grams. So understand, volume taken as 50 ml in this crucible, and then the empty without any water sample, this much is the weight. With water sample combusted or heated at 104 degrees Celsius, this much up, At 600 degrees Celsius, it is fired. So this much is the residue, W3. So what are we? What is the question? So the concentration of total volatile solids is. So this will contain, no. So this will contain organic solids plus inorganic solids. Organic solids and inorganic solids. So here it will contain only inorganic solids. And organic solids are also called as volatile solids. So this total solids, organic solids, inorganic solids. Organic solids are also called as volatile solids. Volatile solids. And these are also called fixed solids. So when we keep them, when we burn them, when total solids is combusted at 600 degrees Celsius, only inorganic fixed solids left behind in the crucible, and these will get at 105 degrees Celsius, around this much, and this will get at 600 degrees Celsius. This is done in the muffle furnace. So here only inorganic solids will be left behind. So difference of these two will give us the volatile solids. Now let's calculate. Volatile solids concentration is W2 minus W3 divided by 50 by 1000 liter. How much is the W2 is 55.129 minus 54.783 divided by 50 into 1000, and this is in grams, and we want it in milligrams. $55.129 and then 54.783 into 1000 into, let's, 1 milligram per liter. So if you solve it, you will get it around 6920 milligram per liter. Milligram per liter. So the answer is 6920 milligram per liter. In the water sample, the concentration of calcium, magnesium ions and bicarbonate ion are 136 and 122 milligram per liter respectively. The atomic masses of various elements are this, and total hardness and temporary hardness in water sample is. So we need to calculate total hardness and temporary hardness. Temporary hardness is also called as carbonate hardness. Temporary hardness is also called as carbonate hardness, and it has total hardness has two components. Total hardness is two components, one is temporary and one is permanent. This is called non-carbonate hardness. This is imparted by carbonates and bicarbonates, and these are important by chloride, sulfate, and nitrites. These anions will impart carbonate and non-carbonate ions. So let's understand. So let's calculate first. Total hardness. Total hardness. In hardness, we'll only take multivalent cations. Multivalent cations here are calcium and magnesium, and their weight is given as 100 milligram per liter. 100 milligram per liter and 36 milligram per liter. So we will convert it in the form of equivalents. So first we'll find the equivalents. So equivalents we'll find equivalents, and then we will multiply those equivalents with one equivalent of CaCO3, that is 50. Then we will get the hardness in terms of CaCO3. Let's understand. 100 divided by 20. So calcium weight is 40. We will take it as 20 because it has 2 valency. Magnesium is 24. We will take it as 12. And then these are the equivalents. So if we want to convert these equivalents in terms of CO3, we will multiply it with one equivalent weight of CaCO3, that is 50. So here it is converted in terms of milli-equivalent. So we'll get milligram per liter only. So 5 plus 3 into 50, we are getting 400 milligram per liter. Why milligram? Because it is also in the milligram. 136 are in milligram. So the total hardness is 400 milligram per liter. Total hardness is 400 milligram per liter. And the second part is and temporary hardness. So there is one more concept. Carbonate hardness is minimum of total hardness and alkalinity. It is minimum. Carbonate hardness or temporary hardness is minimum of total hardness or alkalinity. So whichever is less, that is the carbonate hardness. So total hardness we have calculated. Now let's calculate alkalinity. Alkalinity here is imparted by HCO3 only, and HCO3 has a concentration of 122. HCO3 has a concentration of 122 milligram per liter. That is in SCO3 terms. We will convert the same thing in terms of CaCO3. So it will come out as 100 milligram per liter as CaCO3. So first we will convert it in the form of equivalents. I will call it milli-equivalents, and milli-equivalents into milligram per liter by multiplying it. This is the equivalent weight of CaCO3. And these are milli-equivalents of HCO3. So we are converting the milli-equivalents of CaCO3 into CaCO3 by multiplying it with the equivalent weight. So carbonate hardness is minimum of total hardness. How much it was it? 400 and 100. So carbon hardness is 100 milligram per liter in terms of CaCO3. The answer is 400 and 100. The answer is 400 and 100 milligram per liter respectively. A water filtration unit is made of uniform size sand particles of 0.4 mm diameter. So what is happening? So the water filtration is one of a treatment steps for wastewater treatment. So what is done? So it is filled with the very small sand particles. Very small sand particles of uniform size sand is 0.4 mm. So it is zero point 0.4, not even 1 mm, less than 1 mm, that is 0.4 mm diameter particles. The shape factor is this, specific gravity is this. The depth of sand filter is how much? It is around 70 centimeter, that means 70 meter. And the porosity, initial porosity is 0.35, and the filter is bed is expanded to a porosity of final is 0.65. Uh, so the filter bed is expanded to a porosity of 0.65 by hydraulic backwash, and the terminal settling velocity of sand particles during backwash is 4.5 centimeter per second. The required backwash velocity is. So what is happening? So during the treatment of water, the water is passed through sand, this sand bed like this way. This is during the treatment of water, and during the treatment of the filter. So what, there are two cases: treatment of filter and treatment of water. The cleaning of the filter, the water is passed in the reverse direction, that is called backwashing. So during the backwashing, this height will increase, and if the height increases, there is more space between the particles, and that because of that the porosity increases. So because of this porosity increase, so that to increase the porosity from this to this, so the required backwash velocity. So how much is the backwash velocity? How much is the backwash velocity required to expand the porosity from this to this? That we need to calculate. There is a formula: backwash velocity by settling velocity to the power 0.22. So if we solve it, so we need to calculate backwash velocity. So eta f final to the power 1 divided by 0.22 into settling velocity. So the velocity of so the terminal settling velocity of sand particles. So the particle will go up and then they will come down based on their settling velocity. So that is backwash velocity, and this is settling velocity. The particle, if it comes down, this particle. So the porosity will increase if VB is more, if backwash velocity is more. So that's why it is directly proportional to VB, and the settling velocity will tend to decrease the porosity. So it is inversely proportional to the settling velocity Vs. So we need to calculate VB. So we'll solve it. We will get the VB, and how much we will get. Let me check. VB you will get, after solving, you will get VB as 6 point. This you have to calculate as 0.65. You will get it as 6.35 into 10 to the power minus 3 meter per second. The answer is 6.35 into 10 to the power minus 3 meter per second. Our next question is: a sample of water contain an organic compound this at a concentration of 10 to the power minus 3 mole per liter. Given that the atomic weight are these and theoretical oxygen demand of water, so we need to calculate theoretical oxygen demand. So theoretical oxygen demand is for the decomposition of this compound C8H16O8 in presence of oxygen. So the oxygen demand, so it will oxidize, so this will be oxidized to CO2, and the oxygen will reduce to H2O. So 8 8 carbons will form 8 CO2 and hydrogen are 16, so here 8 we will get. So 8 hydrogen, 8 oxygen will be there and 8 oxygen will be there. So 1 mole of this will require 8 moles of oxygen. So 0.001 mole will require 0.008 moles of oxygen. So 0.008 moles means 10 to the power oxygen is 32. 60 into 2, 32. So this much amount of oxygen is required. Let me calculate. We will get around 0.256 grams of oxygen. This is the answer. This is the new question. The ion product of water is 14. If the rainwater sample has a pH of 5.6, concentration of OH minus in the sample in 10 to the power minus 9 mole per liter, round up to 1 decimal place. This is a great question. So we know that pH plus pOH is 14 and the pH is 5.6, so the pOH will be 14 minus 5.6. So 8.4. So pOH is nothing but minus log of OH minus ion concentration is equals to 8.4. So OH minus ion concentration can be written as minus 10 to the power minus 8.4, but we have to represent it in the form of 10 to the power minus 9, so we will write it as 10 to the power minus 9 plus 0.6, and we will solve it as 0.6 into 10 to the power minus 9. 10 to the power 0.6 is 3.98. Yes, 3.98 into 10 to the power minus 9 mole per liter. The answer is A. Next question is, a river has a flow. So we have a river and wastewater stream. So river has a flow of how much? 1000 mld. I'm writing it as mld, and it has a BOD 5 of 5 milligram per liter, and it has a DO of 8 milligram per liter before receiving the wastewater discharge at the location. Saturation DO level is 10 milligram per liter of the river. So this is about, these are the all parameters for river. So what is happening if you see it, want to visualize it? So a river is flowing And what are we doing? We are discharging the wastewater into the river. So river has these parameters which are written here, and this stream or wastewater has certain parameters that we will see. And what will happen, so if they will mix, there will be a reduction of the DO in the water, in the river water. So what is the deficit? So how much is the difference in the DO level, which was, let's say the DO level was 10 here, and how much is the DO level here after this discharge, that we want to check. What is the difference? What is the difference we want to know? 10 minus x, like, okay, so that we'll understand. So for the existing environmental condition, the saturation DO is 10 milligram per liter in the river. Wastewater discharge is 100 with BOD is 200 milligram per liter. So BOD defines the organic matter strength, and the DO is 2 because organic matter is more. So the organic matter is consuming oxygen, dissolved oxygen. That's why the DO is less in the wastewater. And falls at the location, assuming the complete mixing of wastewater and the river water. So where we are supplying the wastewater, there is, we are telling like there is complete mixing here. Okay. So assuming complete mixing of the wastewater and the river water, the immediate DO deficit milligram per liter around the 2 decimal is. So yeah, we need to know the deficit. So we'll find the DO of the mix. The mix will be, so the DO is nothing but the weighted average. Q of river, DO of river plus Q of wastewater, DO of wastewater, Q of river plus Q of wastewater, DO of the river. What we are saying here, this is the river is flowing. From the outfall we are discharging wastewater. This is the river, complete mixing going on here. Mixing. Let's see what is the DO of mix. It was 1000 into 8 plus 1100 into 2 divided by 1000 plus 100. So we'll get DO of mix is 7.45 milligram per liter, and deficit we will calculate as DO deficit we will calculate it as DO saturated. What was the DO saturated minus DO of the mix? So the DO saturated is given as 10 in the question, and so 10 minus 7.45, we'll solve it and I'll get it as 2.54 milligram per liter. This is the answer. Activated carbon is used to remove pollutants from the wastewater in a mixed batch reactor. So first understand what is batch reactor. In the batch reactor, the water is filled and then there is no filling and then it is closed, and then the process goes on inside the reactor. This is called batch reactor. So in the continuous reactor, CSTR, continuous state, so the water is supplied and it is taken out, and the same time the process goes on. So these are the continuous reactors. So in the batch reactor, water is filled and then the reaction is completed in a certain time and then the water is taken out. So these are the different reactors. There are different type of reactors. One is plug flow reactor. So in the plug flow reactor, it's like our intestine, you can say. So the waste is fed, it flows through that pipe or rectangular channel, and it is the treatment goes on and it comes out. So these are different types of reactor. Uh, Here the process is about mixed batch reactor. So activated carbon is used to remove the pollution from a wastewater in a mixed batch reactor, which follows first order kinetics at a reaction rate of this, and time required to remove the 95% pollutant is how much. So what we are doing, so in the lab you may do this experiment. You are taking the conical flasks, you call them as a mixed batch reactor because this will be put in the shaker table. You have put activated carbon, and let's take you have kept dye wastewater. Dye means I'm taking dye because you can see the color of the dye. Let's say the blue color dye is there, dye, and you have activated carbon, and if you will put it, and after some time you can see the dye wastewater. The color has been removed because the color will be adsorbed on the surface of activated carbon. So this is the system, and so the first order kinetics is like C is equals to C naught e to the power minus kt, or sometimes we write it as nt is equals to n naught e to the power minus kt. First order means dn by dnt by dt is directly proportional to nt. Rate of change of parameter is directly proportional to the parameter to the power 1. So if you solve it and integrate it, you will get these equations. So the pollutant removed is 95% is removed, so 5% is only left. So e to the power minus k is given as 0.38. 0.38 time we need to calculate. So if you solve it, you have to take log 0.05. Log means ln. You have to take natural log. You have to take natural log 0.05 and ln 0.38 into t into ln e, that is 1. So t will be minus ln 0.05 divided by 0.38. If you solve it, you will get time as 7.88 or 7.9 days. This is the answer. So you will get answer as 7.99 days, 7.88 days. So the question is, to remove the 95% of the color, you need to shake it in the mixed batch reactor for around 8 days, and you can see the dye color has been removed. But there are so many things that we need to discuss later. Here we have one more question. A 30 centimeter diameter well fully penetrates in an unconfined aquifer. So let's see. There is a well, 30 centimeter diameter well penetrates in an unconfined. So this is straight, okay. This is the groundwater level table. This is ground level. A 30 centimeter diameter well fully penetrates an unconfined aquifer of saturated thickness 20 meter, with hydraulic conductivity of 10 meter per day. So the saturation thickness is 20 meter. 20 meter. Hydraulic conductivity is K is hydraulic conductivity of soil 10 meter per day. It is written as 100 meter per day. 100 meter per day under the steady pumping rate for a long time. The drawdown and two observation wells located at 10 meter and 100 meter from the pumping well are 5 and 1 meter. So we have observation wells at 10 meter and 100 meter distance. So one observation well is here, we can say, and other observation well is at 100 meter. So, and the drawdown observed is like this. So from the well, if you see the drawdown, it will look like this. The drawdown is 5 meter and 1 meter. This is 1 meter. This is 5 meter, respectively. The corresponding pumping rate from the well. So the pumping rate we need to calculate. Q is equals to pi k h2 square minus h1 square divided by 2.303 log. What is this? This is 100 divided by 10. That h2 will be 20 minus 5 and h1 will be 20 minus 1. We'll see it here. So h2 will be h2 here. First well is at, this well is at 10 meter distance and it has drawdown of 19 meter, 20 minus 1, and at 100 meter it has a drawdown of 5 meter. So using the formula pi k 19 minus 15 square ln this by this, you will get q as this much. The answer is 1850. 1855.5. Simple. In the context of water and wastewater treatment, the correct statements are. This is also a gate question. So in the context of water and wastewater, statements are: particulate matter may shield microorganism during disinfection. Particulate matter. So we need to find the correct statement. Particulate matter may shield microorganism during disinfection. Yeah, this is correct. Ammonia decreases the chlorine demand. No, it increases the chlorine demand. Because ammonia reacts with chlorine and it forms chloramine or combined chlorine. So it increases the chlorine demand. Phosphorus stimulates algal and aquatic growth. Yeah, because phosphorus and nitrogen are the nutrients that causes algae growth. Calcium and magnesium increase the hardness and total dissolved solids. Yeah, correct. Because these two are soluble compounds, so they increase total dissolved solids and hardness also. These are multivalent cations, so that's why they cause the hardness to increase. So these three are correct. So now we have a question related to circular settling tank. So circular settling tanks looks like this. So the water comes through this bottom inlet. The water goes up with the help of a pipe, and it spreads like this, and water goes into the periphery, and the particles settle down like this way. And here we have a hopper. From there, like we have in our cars, we have wipers, they will rotate. So at the bottom we have scraper, it will rotate, and from that hopper we can remove the solids. And the effluent can be collected through this vias at the top. So from the top we can collect the water effluent. So this is how circular sedimentation tank works. Water in, it goes up, and then it comes and the particle will settle like will settle in this trajectory, and the water goes towards the periphery, towards the outlet that is provided in the it is provided it is provided at the perimeter of the uh, clarifier, and from one end the effluent is actually collected. So this is how circular settling tank works, and let's understand the question. So in a circular settling tank is to be designed for a primary treatment of sewage of a flow rate. So the flow rate which is provided here, the Q which is provided here is 10 mld, 10 million liter per day. Assume a retention period of 2 hours. Retention time is, so for 2 hours, so the particle which is entering will take 2 hours to come out. It means 2 hours means this. The retention time is 2 hours, and surface loading rate is 40,000 liters per meter square per day. The height in meters of water column of the tank. So we need to calculate the height. So for calculation, we generally consider it as cylindrical. Q is 10. Q is 10 mld. Detention time is 2 hours. And what else? Sorry. Surface loading rate. Surface loading rate is 40,000 liter meter square per day. Surface loading rate is 40,000 liter meter square per day. So first we'll calculate how much is the volume required from these two data. So volume is equals to discharge into 2 hours. So that is 10 to the power 7. Let's put 10 to the power 3, 4 meter cube per day. I've converted it into meter cube, and then 2 divided by 24 days. The volume comes out to be 833.3 meter cube, and then this is the volume of the sedimentation tank. And if we get the area, we can find the depth. So area can be calculated with this data. Area we get. We know the Q value. Q is 10 to the power 7 liter per day. And if we divide it by surface loading rate, that is 40,000 liter per meter square per day, we'll get the area. That area will come out as 250 meter square. And if you want depth, we can find it as volume divided by area. We know the volume from here. Volume is 833.33 divided by 250. We'll get the depth as 3.33 meter. That is the depth of the circular clarifier. The answer is 3.33. Which of the following statement are true for aerobic composting of sewage sludge? Bulking agents are added during the composting process to reduce the porosity of solid mixture. No, these are added to increase. Leachate can be generated during the composting. Correct. It can be generated. Active mycetes are involved in the process. Yes, these are involved in the process. In vessel composting cannot be operated in the plug flow mode. No, it is operated in the plug flow mode. So 2 and 3 B and C are correct. Thank you. Thank you for joining the session.